In part 2, we did it. We found 2 radioactive radium springs and the smoking gun of a third. It was a tough challenge, but the 3 Haslam grid references were true. Dare we doubt Dr. Haslam? But now we have to answer the questions. Why here and how? Time for a walk and talk by the moonlight. I don't think I've done a piece to camera before by moonlight. So the science. So I'm going to quickly do this while I can actually see. So the science behind what we've seen today. So I explained that the springs were radioactive because they contained radium and they contained radon. And the radon and radium are daughter products of the radioactive decay of uranium-238. And uranium-238 is in the ground in the Cheviot granite. So although the Cheviot granite isn't at surface level here, it is deep underground and it's doing its thing. So that explains the basics of why those springs are radioactive. But why those springs? Well, there's a few answers to this one. So the first thing is that uranium itself is a bit of a tricky customer when it comes to chemistry. So a lot of the elements will form minerals and molecules dead easy. And that's where you get your feldspar and your granites and all these sort of things that are just lovely mixes of different elements. Problem is that the iron of uranium is a weird size, so it doesn't crystallize very well. So what happens is that when the magma cools, the uranium gets left right to the end, like the dregs, if you like. And what tends to happen is that it forms crystals with minerals like zircon and apatite, monazite as well, which then brings in thorium, which is an equally tricky customer. And then they sit in these zircon matrix, living happily ever after. But then what happens is that the uranium, which has a really long half-life, 4.5 billion years, when an uranium atom turns into a radium atom, or the radium atom turns to radon, or whatever the process is, what you end up with is that it's something called alpha recoil. So what happens with radioactive decay? In this situation, you get an alpha particle and you also get the daughter element. And these things have got loads of energy. That's why nuclear power stations work, for example. And they literally fight their way out of the zircon crystal. They punch a hole and it provides a pathway for them to escape. So they then escape and then they are dissolved by the water, because radium and radon are both soluble in water, and they're dissolved by the water that's underneath. That's all very good. So we've got water deep underground which has radon and radium. Great. How did it get to Carlcroft Burn? Well, the exact same process that caused the alpha recoil also produces heat. So the radioactive decay is heating up the water. So you've got a heat source as well as a source of radioactive elements. And for anybody who's had a lava lamp, you'll know what the process is. So hot water rises, cold water cools. So that hot water, full of radon and radium, rises from deep within the Earth's crust into the surface. Sorted. Okay, that's great. So then we have another problem. There's uranium in the peat soil. So that was location number 2. And you'll have to take my word for it at the moment. I'll try and prove it later. So there's uranium in the peat soil. So how did that get there if uranium is trapped in this zircon matrix? Well, it turns out that it's carbon dioxide of all things. So carbon dioxide dissolves in water and it forms carbonates, or the sort of ion for carbonates. Oh, just avoid this puddle. So the ion will readily combine with uranium. So it's one of the few things that it's okay with. So that's all jolly good. The other thing is it's then soluble in water. So the uranium finds its way out of the zircon or the apatite or whatever it's in. And again, just like the springs, just like the radium and the radon, it'll come up to the surface. But there's a catch. So when I was at location number 2, it stunk. And the reason it stunk is because there was lots of peat there. And peat is something called reducing. It's low in oxygen. And the reason it smells is because there's loads of like sulfurous things and nasty horrible things that thrive in low oxygen environments. Now uranium likes to be amongst oxygen. You take the oxygen away and uranium transforms itself from being in a soluble form to an insoluble form. So what happens is that the uranium will precipitate out of the water, and then it becomes trapped in the peat. Now, for anybody who's followed the channel, you will know that the exact same process happens at the Needle's Eye. And I'll leave a link, but in very short terms, there is uranium-bearing rocks on the cliff face. And what happens is that the water brings it down, but the peat then traps it, and it traps it for thousands of years. It's a very, very interesting and impressive feat that it does. So that explains why there's uranium in the sort of peaty soil surrounding the springs, rather than in the spring water itself. Okay, so I think we're nearly there. There's only one sort of question and then one observation left, so I hope you can bear with me. So the one question is, why there? Why at Carlcroft Burn? Well, the answer to that is to do with plumbing. So running roughly sort of east to west across the Cheviots is the Geiger Heart-Hope fault. And it's a massive thing. It goes on for about 10-15 miles. And it is one of the major faults in the Cheviots. And a fault is just a posh word for a crack. And that fault provides the pathway. So if you've got all this water and it's hot and it's rising and it wants to get out, it needs a channel, it needs a way of getting out. And it uses the fault system to get from, deep underground up here. Now, Carlcroft Burn, the area we were in, happens to lie right smack on that fault. So this fault in the earth is deep underground, and it provides the channels, the pathways. If I avoid another puddle. So it uses the pathways, the faults, to get out, and that is why there. Now, Dr. Haslam, who is fast becoming my favourite human in the world, he mapped out several of these, and they all fall in within a quarter of a mile of the fault, and I'll put an image up now to show you his map. So he visited loads of these, and I picked Carlcroft just because it was the most radioactive. So obviously it gives me the best chance of finding it. But there are loads of these. Always close the gates to find in the Cheviots, following the Geiger Heart-Hope fault. So that explains why there, why just every other random spring and bit of water in the Cheviots isn't as radioactive. Now that's not to say that there aren't more, because there's the Breamish fault, there's the College Valley fault, there's loads of faults in the Cheviots, but this is the one which has been studied most. And then there's one final thought that comes out of all of this, and that's why I was taking temperatures, because the water in the springs is hotter than the water. It's not easy with these puddles. The water in the springs is obviously hotter than the water that's coming from the river. You have a temperature gradient. Now you think to somewhere like Iceland, which basically runs on geothermal energy, and there's other places, there's obviously Yellowstone in America. You know, these places run from the heat, and the heat comes, in their case, just from volcanic activity, because basically Iceland's just one big volcano, and you're only like, you know, 6 feet away from an eruption. Here, it's because of radioactive decay. So the radioactive decay is the heat source. So whilst I've only ever found one study, and they said there wasn't quite enough of a temperature gradient to make it feasible, technology moves on quickly, and I'd be very interested if somebody had another look at this, because I just had a crappy £10 thermometer and I stuck it in like one spring or one bit of the river. You know, there'll be people who have got much more sophisticated equipment, and I'm sure if you dug underground, because heat rises, you'd be surprised how hot that would get. So you never know, somebody may revisit Dr. Haslam's, you know, over 50-year research and look into this, because not only are we talking about radioactivity and discovering it and finding it in springs and doing cool stuff, it may actually provide a solution to a problem. You just never know. Bye, Moon.
So we've explained the why. Firstly, uranium trapped inside zircon and other crystals decays into radium, which bursts out. It dissolves in the water, and the heat from the radioactive decay takes it to the surface. The same pathway brings uranium up too, but it becomes insoluble and trapped in the reducing peat bog. The how? Well, nature created a special radioactive superhighway. A network of faults centred on the Geiger-Hartholt fault brings that hot water rich in radioactives to the surface. Carlcroft Burn provides the final step, sitting proud on the biggest fault in the Cheviots. Dr. Haslam's final gift is a map, a list of 50 radioactive hotspots across the Cheviots, 12 in the water following the GHF and 38 in the rock across the district. We could spend a lifetime following the clues, but we're not finished yet. We have science to do. In part 4, we push our skills and equipment to the limit. We test the water, the soil, pore over charts and graphs from the Radioactive, and go hunting for the science. Dr. Haslam promised us radium and radon. What we found started life inside a nuclear bomb. Make sure you subscribe, you're not going to want to miss this.